Hi guys, I made a new video today. It's part 2, or I guess you could say part 3 of my op-amp circuits, and this is just more into analog computing. So in the last video I made a op-amp adding circuit, voltage addition circuit. So in this one I'm making a differential amplifier or a voltage subtraction circuit. So it's constructed like this. There's a voltage divider between your input voltage 1 and it meets at the inverting input, and then there's another resistor that goes to your V out as a feedback, and then the non-inverting input, it has kind of the same configuration, but the second resistor goes to ground. So whatever your input voltage 2 is, this V2 is going to be half of that. So assume over here that we have an input voltage of 3.6 volts, which I have set up over here on the non-inverting input. It's about 3.6 volts. So that must mean that V2 will be 1.8 volts, and I'll measure that for you and show you that. So measure this point and you get exactly 1.8 volts. Now at some point V1 will also go to 1.8 volts, since first of all we have unity gain, and an op-amp likes to keep the voltage difference between the inputs at 0 ideally, which it does perfectly here. So I'll shift this over to the other input, and you'll see that we're at 1.81. So it's not exactly perfect, but it's doing the best that it can. It's not an ideal op-amp by any means. It's a LM358, but that's pretty good. So if that's the case, that must mean that both of these are going to be 1.8 volts. So if we look at this one over here, this voltage divider specifically that goes from your input 1 to the non-inverting and feeds back into the output, you'll see something kind of like this. So we have 2.1 volts over here, then your equivalent value resistor, which I'm using 100K for all of these resistors, and then you have your 1.8 volts, then you have another resistor, and then you have your V out. Now according to the equation, we obviously know that it's going to be 1.5 volts, but that's a little bit too just simple, and I want to show you guys a little bit more why that happens. So if you look here, the voltage drop across this resistor is negative 0.3 volts, and that makes sense because you're going from 2.1 to 1.8, you got a voltage drop of 0.3. So if that's also the case here, which it has to be according to Ohm's law, because this is the same resistance as this one, so it's also got to have a negative 0.3 voltage drop. So you will arrive at 1.5 volts, which according to simple math is true. 3.6 minus 2.1 is equivalent to 1.5 volts. So that's our circuit, and you could ignore a little bit of this math. This math isn't really that necessary, but yeah, that's about it. And I'll just show you guys the circuit built over here, and I'll show you the output. It should be exactly 1.5 volts. Yeah, pretty close. So both of the inputs are the same, which op-amps do. They're supposed to. That's one of the big rules of op-amps. And you could probe each of the voltages. And yeah, so that's pretty much it for this circuit. I'll be trying to make more analog computing videos. And thank you so much guys for watching, and I'll see you in the next video.